This tutorial is designed to help you identify the shapes that molecules will take. And so the main thing that impacts the shape of a molecule is these electron domains. And by electron domains, I essentially mean how many things are there bonded to the central atom. So if we look at this top example, carbon dioxide, CO2, how many things are there bonded to the central carbon? Well, obviously there's two. And so that makes us have a linear molecule, right? So the two things bonded to the central carbon are going to try to get as far away from each other as they possibly can, which is 180 degrees, and that gives a linear molecule. So moving on to the next example, BF3, right? So boron is sort of a strange atom in the fact that it doesn't need to satisfy its octet. So we can look at boron and say how many things are bonded to this boron, and then how many things are there? The answer is 3. And again, just like for carbon dioxide, they're going to try to get as far away from each other as they possibly can, and the angle they do to do that is 120 degrees, and the shape is going to be trigonal planar because it's making a triangle-like shape, and they're all in one plane. Moving on to the next example, methane, CH4. We can ask again how many things are around that central carbon, and the answer is 4. We're moving up. And now we can say how far away can these things get from each other. You might be tempted to say it's 90. Well, it's not, because atoms rather, can be in three-dimensional space. So it's better to think of this methane as having a carbon with 2 hydrogens that are all in the same plane here, and then 2 hydrogens in a different plane, so coming in and out of the screen, which I'll draw by these dashed and wedged lines here. And when you do this, right, we can get the atoms actually 109.5 degrees away from each other. And this shape is called tetrahedral. Now, the next question that comes into play is what happens with lone pairs. So we can move on to ammonia and H3, and we ask how many things are there around that central nitrogen. And the lone pairs are things, so they count as things. So there are still 4 things, and we have a base tetrahedral geometry. However, when we talk about geometry, we're really only talking about the atoms. We don't care about the lone pair. So if we were to look at this in 3 dimensions, it's like we have a nitrogen with a hydrogen, and then we have a lone pair in the same plane as the hydrogen, and then we have another hydrogen coming in and out of the screen. And the shape that this gives us, just looking at the nitrogen and the hydrogens, is called trigonal pyramidal. Because it's triangular just like the trigonal planar shape, however it's not planar, it's pyramidal. Now we can move on to water, H2O. We can ask the same question, how many things are around the central oxygen? And there's still 4, right? Lone pairs are still things. And the way that's going to look is like this. And now these lone pairs are in a different plane than the 2 hydrogens, and this is a bent molecule. What is this going to do to the bond angle? Well, it turns out that lone pairs take up a little bit more space than bonds. So what that does is it smushes all the atoms together. So for the trigonal pyramidal ammonia, rather than having a bond angle of 109.5, it has a bond angle of 107. And then water with 2 lone pairs is even more smushed together and has a bond angle of 104.5. Well, what about ozone? So I have O3, the Lewis structure out here is drawn. So how many things are there around that central oxygen? Well, there are 3 things. Right, if we're looking at it in terms of how it would look dimensionally, right, we have 1 oxygen, we have another oxygen, and we have a lone pair. What shape is this? Well, it's still a bent molecule. What would the bond angle be? We would expect the bond angle would be a little bit less, not than 109.5, but a little bit less than 120, because it's based on trigonal planar, because there are 3 things around that central oxygen. And that is what we find the bond angle is about 117 degrees. And there are a few other shapes that the reading went into. I'm not going to go into them so much here. These are what happens when you have an expanded octet, but I'll go through a couple examples here. So we have PCl5. So how many chlorines are around that central phosphorus? Well, there are 5. And what does that geometry look like? Well, it turns out that we have one central phosphorus, and we're going to have a trigonal plane here of chlorine. So we have 3 chlorines making a triangle plane, and then we have 2 more axial chlorines. And the bond angle here is 120 degrees between the chlorines and the triangle plane, and 90 degrees between the axial ones and then the ones in the plane. And the shape of this is trigonal again, because we have this triangle plane, and then it's bipyramidal because we're making 2 pyramids. The last shape we have is SF6, so there are 6 fluorines bonded to a central sulfur, and that looks pretty similar to the trigonal bipyramidal, in which we have another plane. However, instead of having a trigonal plane, we have a square plane, right, with 4 fluorines, and then we have 2 axial fluorines as well. And here, the angles for all all these fluorines are 90 degrees. And this shape is octahedral. But we're not going to focus too much on the extended octet, and really I want you to know how to make and be familiar with these shapes. And so what's important to know, again, as a summary, what we're caring about is how many things are around the central carbon. So if there are 2 things around the central carbon, we have a linear molecule. If there are 3, we have a trigonal planar or a bent if one of the things is a lone pair. And then for 4, we have tetrahedral, trigonal pyramidal if there's 1 lone pair, and bent, again, if there is 2 lone pairs.